in selling equipment worldwide. So he is a specialist in high-end, ultra-high pressure homogenizers and producing technically elite solutions. So we have with Mark, Freeman, even with his busy schedule, I'm just asking him how the things is going on. But even in this pandemic situation, he is running around the country, around the global level. But somehow, he made a time for us for explaining about the homogenizer, especially for the high pressure homogenizer. Heartily welcome, Mark, for your next session, probably 40-45 minutes from your end. Most welcome.
Okay. Okay. Thank you very much for your very kind introduction, and thank you very much for giving me the opportunity to talk to the meeting. So as you said, I now run company Homogenizing Systems. We're a UK based company, but we work globally, and we have a very large presence in India in particular. So why is that not working? Let's try that. Okay. So we're based between London and Cambridge in the UK. But as I said, we work globally. So in this presentation, I'm going to talk a little bit about the company. I'm going to spend some time on the fundamentals of high pressure homogenization, system construction, and the processing technology. I'm going to then tell you a little bit about our range of equipment, and then I'm going to talk a little bit about some of the applications of high pressure homogenization and how some of those are related to food and nanotechnology in the food arena. So the company Homogenizing Systems Limited is actually quite a new company, only founded in 2017, but is a spin-off of the Stansted Fluid Power Products Group. So it's a subsidiary company, and Stansted Fluid Power Products Group, we've been manufacturing equipment for more than 45 years. It's about 50 years of design and manufacture now. And Homogenizing Systems manufacture and support the Stansted range of homogenizers, which is a range that at origin dates back about 40 years, but we've been doing a lot with it in the last few years in terms of technical improvements. So I'm going to be talking in megapascals if I make any reference to pressure. To make it easy for you, if you think in bar, just add a naught onto the end. And if you're old-fashioned enough to think in PSI, well, 100 megapascals equals 15,000 PSI, more or less. Okay, and I've just put a little table up here. You can see typical car tires are going to be 0.2 megapascals. If you were doing diving or welding, you might be experiencing 20 megapascals. But when we get into the high pressure homogenization, we're generally in the 100 to 400 megapascal range. And I would think 400 megapascals is quite high pressure, but when I talk to people who make synthetic diamonds, like the ones we use in some of our equipment, they would think our pressures are quite low. They'll be often working up at 5,000 megapascals. So pressure is a little subjective, but by any standards, 400 megapascals is a very high pressure. So why do we want to use a homogenizer? Essentially, we're looking to break particles down in size and control the size. And what we're doing effectively with high pressure is using the energy of the pressure through the application of shear, impact, and cavitation to break the particles down in size, increasing the surface area effectively. So if we look at homogenization in general, well, we could start at the most basic level with a whisk, and then we might move into some other technologies such as ultrasonics or high-speed rotor stator devices. Now, these will all achieve to a greater or lesser extent homogenization. And if you were just making a mayonnaise for your food in the kitchen, the hand whisk might be good enough. But as we need to put more and more energy in to create smaller particles, we need different devices, and ultrasonic and high-speed rotor stators are an intermediate energy supply, but when these run out of power, that's when we switch to high pressure. So I would never tell anyone to use high pressure just for the sake of using high pressure. Use high pressure when other methods are not effective. What is a high pressure homogenizer? Well, it's very, very simple in concept. It's a high pressure pump connected to a processing head, which we would normally refer to as a valve, but can be a fixed orifice type device. The pump is used to generate pressure in the product, and then as the product passes through the valve, there is an energy transfer and breaking the products down into smaller particle sizes, or in the case of a cell rupture application, into breaking the cell wall membranes. So I've pictured here, just to show a little bit of less bias, a number of systems. The two on the left use what's called piston gap technology, which is the traditional dairy homogenizing type technology. And the two systems on the right, one is one of our competitors, and the one in the top right hand side is one of our own Stansted systems. I could place our own system between the two because we are perhaps unique amongst suppliers in producing systems that can work with piston gap and microchannel technology. So what are the advantages of the high pressure homogenizer? It's really effective at cell rupture, at particle size reduction, can be applied from laboratory through pilot and into production applications. Primary disadvantages are just going to be cost. Compared with a hand whisk, a high pressure homogenizer is certainly a very expensive tool. Compared with a ultrasound or a high-speed rotor stator device, again, it's going to be comparably expensive. But it has the power and the ability to do jobs that they just can't do. The other thing that you should never lose sight of with a high-pressure system is it will need some maintenance periodically. It's a high-pressure device. It has seals and valves, does need to be able to be maintained. So I've said the homogenizer is essentially two elements, a pump and a valve. And there are essentially two types of pump. On the left, you can see an animation of a cranked piston pump like used in a dairy homogenizer. And on the right, you can see an intensifier type pump. Intensifier type pumps are what we use. They're the right solution for very high pressures. The cranked dairy type pump on the left is fine for modest pressure applications, very common in dairy applications, but not really the right tool when we get to the very high pressures that we work at. So, but there is a reason to use a piston plunger pump on occasions. Its advantage, it's low cost, it's efficient, and when they are multi-piston pumps, and dairy homogenizers are often 3, 5, or 7 pistons, they give a very smooth delivery of product. The disadvantage is really its reliability. They are fast running pumps, and fatigue is an issue with high pressure pumps. So if you run these pumps for dairy technology, 35 megapascals, not an issue. But when you start pushing this technology above 100 megapascals, then you start getting into fatigue issues, and the higher the pressure you go, the more those fatigue issues become a real limit to how well you can work with the technology. Additional disadvantages of the piston plunger pumps: they're really not good with high viscosity product because the piston speed is so fast that it cavitates on suction. They are not suitable for use really with fixed orifice devices like microchannels. And as I've mentioned, reliability is dropping off. You will see them sometimes in the lab up to 200 megapascals, but to be honest, I would have my skepticism about the merit of using at that pressure, and in industry I really don't like to see them used above 100 megapascals. The intensifier pumps, reason we use them is fatigue life. Excuse me. So with slow running intensifiers, we have a much better fatigue life because they have a long time, 2, 3, 4, 5 seconds to suck the product in. We have little issues with this higher viscosity product, and we can work with them in our homogenizers up to 400 megapascals. In other parts of the group, the Substantial Fluid Power Products group, we use the same technology all the way up to 14,000 megapascals. Primary disadvantage is just it's more expensive to make an intensifier-based system. Yeah. So we start to look a little bit at the range from our company, Homogenizing Systems. We have on the left a benchtop model, and on the right a triple module production system. So it's important to understand what our philosophy is when it comes to the design and manufacture of high pressure homogenizers. So as I've explained, a high pressure homogenizer is a pump and a processing head. So the pump is the beating heart of the system. If you have a bad heart, it's not good. So we invest a lot of time, materials, and engineering into providing the most robust and reliable pumping system that is available. And then our philosophy in terms of the processing head differs from other manufacturers. Other manufacturers will either offer piston gap technology or microchannel technology. Our experience over 40 years is that no one technology is optimal for all applications. So we produce piston gap and microchannel technology, and we use whichever with the customer is most appropriate. And some customers will even have both technologies on the one system. So I've referred to piston gap and microchannel. On the left is one of the standard reverse flow piston gap valves. Now in operation, the gap as shown will change as a function of flow rate from the pump, pressure from the pump, and viscosity of the product. But as the product passes from the top to the bottom, it passes from high pressure to low pressure. And as it goes past that point, which is labeled gap, it will go from perhaps 200, 300, 400 megapascals to a pressure of 0 or virtually 0 in the space of a fraction of a millimeter. And as it does so, it sees high shear, and all these devices are effectively high shear devices. That shear breaks the particles down and the product then exits the system. On the right, we show a microchannel device. Now, on a microchannel device, the channels are fixed. So where it's indicated micro channel, that passage will never change relative to pressure or temperature or viscosity of the product. So we pass the product in, comes in this case down two feed lines, one on the left, one on the right, and then passes down these channels where it's subject to high shear. We then, in what's called a Y, this is a Y configuration. And then in this section here, we have a mixing of the high velocity fluid jets, and then the fluid exits the system. So we have standard and custom configurations. With our micro channels and our piston gap valves, they're easy to maintain, and you can open them up for cleaning and maintenance and inspection, which is not the case with all suppliers. So come back to the piston gap valve. Piston gap on the right, taken from a dairy homogenizer illustration, is a traditional piston gap valve as was originally developed more than 100 years ago for dairy applications. The left shows our reverse flow piston gap valve. Good things with piston gap valve is you get the full flow of the pump. The gap can adjust itself to related to the pressure, the flow, and the viscosity. So piston gap valves are very good in a lot of applications, cell rupture, dairy homogenization. But when you are looking to achieve the nano scale, they're not always as effective as the micro channel devices, but they're unlikely to block, and they can be scaled, but one has to be a little bit cautious when scaling piston gap from lab to production, just to make sure the processing effect is consistent. With the micro channel device, it's a fixed orifice device, which means for any given pressure, flow, viscosity, you can only get a certain amount of product down the channels. So we can scale this by adding more channels into a device. It's fairly straightforward. It is the go-to technology for the smallest nano emulsions and particle size reduction applications. But because the channels are quite small, we're talking sizes of channels around about 100 microns, so about 1/10 of a millimeter in section, they can be blocked easily by agglomerations of particles if good precautions are not taken on this product. So what should we consider? If you can't achieve the particle size you're looking to achieve, there's no point doing the work. So you have to have enough energy in the system. So if you can do that with an rotor stator device, that's fine, use it. But if you need the energy of a high pressure device, then that's the way to go. I've said that no one homogenizing process is optimal for all applications. So, choose the process that is the best one for your application. And if one type, as I said, if one type of device works and the other does not, then use the one that works. And if I were looking at an application when I'm advising customers, if I have an application where piston gap and micro channel both work equally well, then I will normally recommend the piston gap device because there are fewer issues related to blockage. Some other considerations, particularly in the pharmaceutical arena and nutraceuticals. Can you inspect the internals of the device? With our Stansted range, you can easily dismantle, inspect, and look at them. Some of our primary competitors are sealed for life units. When they block, they're scrap, and you can't open them and see the condition, and you can't maintain them. So our channels, we can maintain them. We can swap the channel elements for different configurations to suit the application. And I've got here, should you use a combination of devices? Well, a typical nano emulsion application will use a high-speed rotor stator device to do a pre-mix prior to using the high-pressure homogenizer. We have other applications where we may pass the products initially through a piston gap valve to do a first level of homogenization prior to putting it through a microchannel device to get the absolute smallest particle size. But the first process reduces the risk of blockage. As I've said, if you don't have a good pump in your system, it's like having a bad heart. So we put a lot of emphasis onto the pump quality, pump reliability, and ease of service and maintenance. If you need to use micro channels, then you need to use intensifier pumps. So if the pressure is low enough and piston gap is suitable, such as dairy homogenization, then a plunger pump, which is not something that we make, is a good option. And I'm happy to recommend customers to that technology if it's the right technology for their application. However, if the pressure is going above 150 megapascals, I really consider the intensifier pump has to be the way to go. You have a little bit of a gray area between 70 and 150 megapascals where we're in the crossover between should it be a piston plunger pump or should it be an intensifier, and that's best assessed on a case-by-case basis depending on the application. And I've said, pumps will need maintenance, so you need to think, is the pump system easy to maintain? Do you have technical support for the pump if you need it? Okay, I'm going to leave the last 2 points. They're a little bit in depth. So the other consideration that you may need to give to your product is excuse me, to do with temperature. So for every 100 megapascals of processing pressure, assuming the product is essentially water-based, you'll get a 22-degree temperature rise. And that's not something you can change. It will occur. You can add cooling in to reduce that temperature rise, but it's something that if you have a product that's temperature sensitive, you need to give consideration to. Some liposome products, like solid lipid nanoparticles, they will normally require to be heated prior to the homogenizer to get the lipids above their melt temperature, and they're going to get even hotter as they go through the homogenizer. And then there is a process, ultra high pressure homogenization, using that as a preservation technique, normally around 250 to 400 megapascals. And that deliberately uses the temperature effect to achieve sterilization temperatures. So typically product will come in at about 50 Celsius as it goes through the homogenizing valve. In a 0.2 of a second, it will go from 50 to 120 plus Celsius, and you're at sterilizing temperature, but with a very short heat up time. You also need to look at any process, how many passes will it need to achieve the particle size. Some processes will work in a single pass. Other processes can take multiple passes. We're involved in some pharmaceutical work in India, production pharmaceutical. The customer there is using 20 passes plus to achieve their particle size, which seems a lot to me, but I recently started work in 2D materials, graphene, and some of those are requiring up to 100 passes to achieve the results. And then ultimately, when you look at scale up, you need to think about the size and the capacity of your system and how it relates to energy consumption and maintenance. So there's a lot to think about when you go to scale up. As a rule, if you need multiple passes, then the lower the pressure, the better for those. I've mentioned before viscosity. You need to keep a really close eye on viscosity, particularly when scaling up and having long pipe runs to the equipment from feed vessels, because if you cavitate flow into the pump, you will cause a lot of damage to the pump, high maintenance requirements. So needs to be careful in terms of pump feed, and the viscosity will limit what you can put through micro channels and how effective product is passing through piston gap valves as well. So it needs to be looked at. Sometimes it's better to run a slightly lower viscosity and concentrate after the homogenizer rather than put too high viscosity through the homogenizer. Safety is important. We're talking high pressure systems here. Well-designed systems will be well protected from a catastrophic failure and give the operator some protection from any aerosols or jets that could be generated from leaking elements or burns from hot surfaces if we're running the systems hot. You will notice that all homogenizing systems, high pressure homogenizers, are fully encased. So our product range, we go from volumes as low as 1 milliliter to large industrial scale processing systems. The range was originally established in the 1970s, but we have been continually evolving it with a lot of evolutions occurring in the last 2-3 years since I started homogenizing systems and could take technical developments in particular directions. So we have pressures up to 420 megapascals. We use both microchannel, sometimes referred to by some manufacturers as interaction chambers, piston gap valves, and also fixed orifice devices. And we look to provide highly controllable systems that give repeatable results, and when transitioning from lab to production, scalability. So we established in high pressure homogenization since 1973. The primary ranges now are the SPCH and 7575 ranges, which are ranges that were developed in the last 10 years. And in fact, there's an error on the SPCH. Those systems are also capable of 4,200 bar. So benchtop model, pressures up to 420 megapascals, flows up to 0.2 liters a minute. Typical minimum volume 5 milliliters. Process maximum volumes on the benchtop systems usually below 10 liters. We do have some special adaptations down to 1 and 2 milliliters. We can run both microchannels and piston gap valves through the systems, and we have a lot of temperature control features for feed and outlet, and even the pump barrel as well. And then we move into the pilot production scale. So these you can see are a little bit bigger. The ones shown in this picture are 7.5 kilowatts, and they feature a number of things. So we have twin intensifiers giving a smooth delivery of flow. We run very slowly, particularly by comparison with others. So not usually running more than 6 strokes per intensifier per minute. We have incorporated now the Siemens Cymatic HMI touchscreen linked to a Siemens PLC. That gives us good functionality, particularly in pharmaceutical applications where we need audit trail capability. We can run microchannel and piston gap processing configurations, and we can install both onto the same machine if required. Stainless steel frame with fully enclosed doors and interlocks, and pressure and temperature displays on the HMI with the ability to data log that with trend charts, and tri-clamp inlet outlets commensurate with food and pharmaceutical applications. Additionally, we have options including heat exchangers, particularly outlet heat exchangers, feed pumps for applications where it's appropriate. We can provide electro polishing and full material certification, offer customers design qualification, installation qualification, and operational qualification. We can provide 21 CFR Part 11 compliance onto the software. We have options for clean in place and steam in place, and we can automate numbers of passes and provide multi-stage processing. So again, we just see the simple animation of a twin intensifier system in synchronous operation. And this is how we provide smooth pulse-free delivery. And if we look on the display here, this is a system running at 200 megapascals, and you can see a little deviation in the gauge as each intensifier swaps over about every 5 seconds. We've actually set the overlap to show a little deviation. Otherwise, if the gauge was dead steady, you wouldn't be able to tell very much from it. And then we take those modules and put them into 1, 2, or 3 module systems. And system shown here is a triple module. This particular one is working at 270 liters an hour, 200 megapascals, and there are 2 of these installed with an Indian biopharma company for their production work. Again, we can work with piston gap and interaction chamber technology, microchannels on these systems. Here's another example. This is in a Chinese production pharmaceutical application, slightly older model predating the HMI touchscreen interface. So what do I consider the primary advantages of my company, the one that I run and the one that I'm technical director for? Well, superior engineering. When it comes to making high pressure equipment, it's all about the engineering, and we provide a better pump construction, which gives better fatigue life, and we have more pressure capability than any other high pressure homogenizer company currently supplying equipment. So most companies are limited to about 200 megapascals. We have capability up to 400 megapascals. Now, I explained high pressure homogenization is an energy conversion game. So we're using the energy of the pressure to put energy into the product to reduce particle size. So the more pressure we have, the more energy conversion capability we have. So it's not always, good to increase the pressure, but we have that pressure capability to give more power for processing to our customers. We have more versatility. We are not fixated on piston gap or microchannel technology. We have developed excellent technologies, market leading technologies with both of these techniques, and we provide whichever is appropriate to the application, and we configure those either in standard configurations or we will customize to suit the application. Our systems are generally lower cost of operation than our competitors' systems, normally also a lower capital cost also, but the medium long-term cost of operating our systems is generally much lower than others because of our better reliability, and frankly we have a fairer pricing policy for spares and maintenance than many other suppliers. You have a very personalized service wherever I'm working in the world through my representatives. It's a very close relationship between us and them, and I choose representatives who can provide excellent technical and maintenance support. And you cannot find a better example than BioZ Engineering in India, who have a dedicated team just supporting our product and who have a lot of expertise and experience in applications with our customers and in supporting our customers with the systems. So we've covered all of this already, but when you come to think about what you're going to do with a high pressure homogenizer, the areas that you're going to have to consider: the flow rate, the application pressure, the single or multi-pass is required, what temperature control you're going to need. Keep in mind that pressure and flow rate determine the power, so the higher the pressure, the higher the flow rate, the more power you will need. And to put it in perspective, 1,000 liters an hour at 400 megapascals is round about 100 kilowatts. So if you want to start doing 10,000 liters an hour, you're into megawatt powers, and that's very large power systems for this type of high pressure system. We said pressure determines the appropriate build, whether we choose, piston gap or plunger pump or intensifier pump. And then, do you need CIP? Do you need SAIP? And who will do the maintenance support for you? So we come on to some applications. One of the most common is cell rupture, where we have many years of experience dating back to the 1970s. Emulsions, dispersions, deagglomeration, and we have been working with for about 15 years. Ultra high pressure homogenization for food preservation and structural modification. Probably 85% of the global work that's been done in this area has been done with our systems. And this is an application that is seeing an increasing amount of interest amongst food industries. It can achieve full sterilization.
Mark, sir would like to talk to you
something. Structural
hi, Mark. Hello.
Changes that can occur from the high pressure homogenization process. There's also use in protein folding and unfolding.
Mark, can you hear us?
High hydrostatic pressure adaptation.
Okay, I think he's not able to listen us.
No problem.
Liposomal products, you can see on the graph, we can reduce liposomal preparations down to sub 100 nanometers. The particular example shown there, the mean size is around 58 nanometers, and that's just in 2 passes, and compared against a competitor system running at 180 megapascals doing 6 passes. So oil water emulsions, very common application of high pressure homogenization across food, pharmaceutical, and other applications, and definitely where applications where we're working in the nano range, sub 100 nanometer oil water emulsions are quite common now. There's further applications of oil water emulsions in cosmetics, and other applications. So I'm just going to skip through that. Low solubility dispersions, the high pressure homogenizers can be used to really break down particle agglomerations. You have to be very careful when we do them because they are solid particles dispersed, and we need to ensure that we don't block microchannels. And this is definitely an application where the microchannel will normally be more effective than a piston gap valve. We've mentioned cell rupture, E. coli, intracellular membrane protein work, quite common, yeast, quite common, and then there's a number. And microalgae now is becoming a subject with gaining a lot of attention, a lot of interest, particularly in the food industry. People are looking at microalgae applications. I'm just going to skip through. I should say I'm not an applications expert, so I tend to have a little less to say on the applications than I do on the equipment, which is my own area of expertise. Solid lipid nanoparticles, again, a very good application of high pressure homogenization, does require some elevated temperature processing and seems to work equally well on piston gap valves as microchannels. And so generally I would recommend a piston gap valve for this application. Polymer chains such as polysaccharide, by passing polysaccharide solutions through a high pressure homogenizer, we can reduce the molecular chain lengths significantly. And we have production applications in India for pharmaceutical companies and working with both piston gap and microchannels, just depending on what the customer's trying to achieve. A fairly new one for me, I only really came across this a few months ago, is 2D materials. High pressure homogenization is an effective and patented method for producing graphene from graphite, and there's work going on more than 2,000 other 2D materials as well. So it's a bit of a buzz in the high advanced materials world, maybe not at the moment so much a food application, but it's just another application of high pressure homogenization. So I have a little bit of information here, and I've referenced my Turkish partner Hacker Science, who provided some of this information for me. So why do we want to go down to the nanoscale? Because it's a greater area to volume ratio, and so it can bring about physiochemical changes, and which can be used, for encapsulation and giving stability and controlled release and enhanced solubility. So I'm really just reading this back off, so you're as welcome to read it as I am. So it's, seeing an increasing number of applications into this area, and being given an example of, using nanoparticles for food safety sensors, encapsulation, controlled release products.
Hi, Mark. Are you able to hear us? Hello? Mark?
So,
Mark,
nanotechnologies are being developed.
No, I think he's not listening to us.
We're involved in 3 or 4 projects.
I think Mark has muted his speaker. Yeah, sorry.
Time
It's
with
okay.
Hacker,
It's okay. Let him finish maybe another 5 minutes.
for
Okay, sir.
food
Thank you, sir.
carrier systems for delivery of nutrients and supplements, organic nano-size additives, food packaging for coatings and improved mechanical and functional properties, nano coatings on food, and food contact surfaces, and nano-sized agrochemicals and sensors. So you can see some applications into packaging with increased strength, lightweight materials, resistance to heat, antibacterial coatings for cooking utensils, color changing contamination sensors, reformulation for more easily absorbed nutrients, products with lower fat, sugar, salt content, improved taste and texture. And there's a reference to nano barcodes at the end. I'm aware that I need to wrap up fairly soon, so I need to just process through these. I'm just going to leave you to read those for a few seconds because, as I say, this information is largely information that is passed to me and I don't have so much direct knowledge of. So there's some examples here of products with nano elements to them. So you can see there a few examples, and there's, I am well aware, quite a lot in development at the moment. So some example on the left here of a nano sensor on the packaging, and on the right here is a reference to the fact that Unilever have developed some low-fat ice cream using nanoscaled emulsion particles. Okay, again, a few more applications here, and then so, there's a lot of work going on in liposomal preparations. We have ongoing work in UK, Turkey, US, India, China, Australia at the moment, most of which, I have to be honest, I don't understand. And even if I did understand, my NDAs with customers would probably stop me talking very much about them. So let's move on. So comes from some work done in Spain with a customer for submicro encapsulation, 400 megapascals, in fact, through a piston gap valve. And there's an example of the product that they produced and were working on. And you can see the casein submicron microcapsules there. So this is some work I did myself a week or two back with a CBD nanoemulsion. CBD is getting a lot of attention at the moment. So on the left, having processed multiple times through the homogenizer with a microchannel, we're around about 20 nanometers, and on the right, we're around about 200 nanometers with the sample. So some summary of the food application: stable nanoemulsions, high concentrated emulsions, high concentrated dispersions, improve color, texture, and taste, slow release, and packaging applications. So in India, oops, seem to have dropped through. As I've said, we are very well represented by BioZ Engineering, and primary contact there is Sudhir Rai in the Mumbai office. So BioZ, established in 97, incorporated 2007, works in a lot of biotech and life science and chemical industry applications, has a very strong technical team and sales team and after service support team. They're very, I can vouch for the fact they're a very professional company, working with a lot of very prestigious customers. They're very experienced with the technologies that they represent, and they invest time and energy into taking training with their principals, such as us, to make sure that they're very well able to support the product. So have a good network across India with offices in Mumbai, Delhi, Hyderabad, and some satellite offices elsewhere. They're working in bioprocess with us in high pressure homogenization, with lyophilization, analytical equipment, process safety, and laboratory design and engineering. Very versatile company, but not over diverse, very specialized in the areas they work in. They work across a number of industries: pharmaceuticals, chemical, food, environmental, work with research institute, governments, academia, and industrial companies. So you can see a sort of overview chart here from them. A little bit more information on some of the products that they work with. So, and just reference to our own high pressure homogenizer, you can see that we have a good installed base in India. I suspect there actually would be more pins in there these days, but we have a very good population of instruments in India, and the BioZ team are very excellent in supporting those instruments. So so I'm just leaving you to read these. This is some of the other systems and instruments and processes that BioZ work in. So they are in food processing. They have pulsed electric field equipment, some high hydrostatic processing pressure equipment, which is supplied by another one of our group companies, Sovereign Pressure Products, which makes high pressure food processors, the high pressure homogenizers from homogenizing systems, and freeze drying. So we have a number of market segments and applications, and you can see covering a good
Hi, Mark.
area
Can you hear me?
application, and particularly drug discovery, development, formulation development, and process development. And you can see a very impressive list of companies using BioZ supplied technologies. You'll see here a list of their primary principal partners, which I'm pleased to see my own company at the top, but a number of other very high quality, very prestigious suppliers you can see, but not an overextensive list, a controllable and specialized group of companies that they can very ably represent without over diversifying and being too diluted in their abilities. Heka Science is our formulation partner. They're based in Turkey, but working with us on projects globally. They can provide consultancy. They have a formulation laboratory, including our high pressure homogenizers, and they have spray drying and other technologies there. So a good company to be able to assist with formulation work, either independently or through ourselves and BioZ. Okay, I think that takes me to the end of the presentation. Apologies if I skip through what is maybe the most interesting area for you, which is the applications, but it's not my strongest area. Okay.
Thank you, Mark. Can you stop sharing the slide, end slide? Can you stop it, if you don't mind? Can you stop it? Mark, can you hear me?
I can't hear anything.
Mark, you are not using earphone, I believe so. Can you hear?
I think
He is not able to listen us. Yes.
I think I will
He's not
call
able
Mark.
to listen.
I will call Mark on a mobile phone and tell him to unmute it. One
Can you
minute,
hear
please.
me?
Yeah.
Yeah, we are hearing.
Mark, can you hear us?
No, Mark is not able to hear us.
1 minute. I'll just unmute.
Hello? Hello, Mark?
Hello?
Mark, people are trying to talk to you on Zoom, but you're not able to hear anything.
I
Can you
can't
unmute your speakers?
unmute or mute.
No, he did muted now. He has muted. Ask him to unmute.
Now, Mark, are you unmute? Are you, Mark? No, I think yet.
Unmute, please.
Wait.
Doctor, I have asked Mark to unmute, log out and log in once again because he was not able to hear any conversation from our side.
Correct. No, better is supposed to close this stop sharing.
Okay, sir, sorry, apologies for this communication gap. He's called him on a private phone. So hopefully, 1 minute.
No, he has to stop share.
He is logging out. I have asked him, requested him to log out.
Can you call him?
Will we call you?
Okay, I will call him. I'll call him. Okay, just
Yeah,
1
now,
minute.
now he has did. Yes, fantastic.
Okay.
He has to
I
log
think
in
we're good.
again. Yeah, he has to,
Yeah,
to log in. Yeah. Now
Correct.
he has logged out. He's supposed to log in now. Let's wait for a minute.
So whilst Mark logs in, and if we have anything specific, we can
Yeah.
try to help out. Yeah.
Yeah. Still, there are a couple of questions. Either Sudhir or Himmat, you can just very simple questions. So you can help us.
We can try to help as much as possible, and in the meanwhile, Mark logs in. Yeah.
Yeah.
Mark logged in. Yes, correct. Yes, please go ahead.
Okay, how can we overcome setting of solids like a cocoa or high protein drinks made with milk? Even after homogenization, is there any solutions of that?
So there are two ways. I think one way is to do the experiment with various pressures and various kind of microchannels. Are we talking about agglomerating of the product after the homogenizing process, or we are talking about sedimentation? So many times we have come across applications wherein the products get settled at base, sedimented at base, but by changing the type of microchannels, we have come across this situation.
Yes. Homogenization is nowadays in many food processing industries, especially in dairy industries. Is it so?
Right. Right. It's very common. In fact, the homogenizing system started its process from the dairy industry, wherein the fat content of the milk had to be emulsified back to not get separated from the milk. So I think the first usage of high pressure homogenizer in the food industry was patented by a company named Gowling somewhere about 150 years back, and they started doing milk homogenization. And still, milk homogenization is a very common practice, a process which is being used by most of the dairy industries. But their application requires much lower pressure as compared to the rest of other things. Probably the milk homogenization happens at 3000 to 5000 psi.
Okay, now
I
Mark
think
is online. Yeah,
Mark is
Mark is
back. Mark is
online.
back. Yeah.
Can you
Are you?
hear me?
Yeah, Mark, sorry for something which has happened.
No, I don't know. It's probably my end.
Yeah,
But
really, we're very sorry. Can you turn on
I
your
don't.
video, Mark?
I don't know if I can. Where's the video? Not can't start video. Okay.
Yeah, it's
Okay. There
fantastic.
you go.
Yeah.
Sorry
So
about that.
there are a couple of questions. Is already just explained by the Sudhir also. There are a few questions I'll just share with you. Is it possible to reduce the size of pesticides into nano size by using high pressure homogenizer?
Reduce what size? What? Sorry. Can you repeat?
Is it possible
Yeah.
to reduce the pesticides, that means liquids, into
Yeah.
nano size by using high pressures?
Yeah. So if pesticide. Yeah. Yeah. Sorry. So I've got a lot of noise in the background of my computer fan at the moment. So sorry about that. Yeah. If the fundamental size of the product is capable of being reduced, and I see no reason why a droplet can't be reduced in size, then yeah, it should be possible. If it was an agglomeration, you might have a bigger difficulty, but if it's a liquid product, it should be possible to get down to the nano size.
Yeah.
But
Yeah, sorry to interrupt, Mark. Dr. Sharan, in fact, here I would like to mention that one of our customers have, done some experiments on pesticides, but their experiment was based on nano emulsions
Yes.
to increase the stability and, more effectivity. So some of the customers have been able to reach to create nano emulsions for the pesticides, and it's working pretty well.
Okay. Okay.
So yeah, I mean, I would concur with that. If it's a nano emulsion, you can certainly anticipate to be able to get into the low nano size range. I mean, below 100 nanometers is very common in oil water type emulsions. So as you saw from my presentation, with some CBD emulsion, we were down to 20 nanometers.
Okay, so there is another question. Is it the same basic principle works good for all the homogenizers?
No, the answer is no on that. Is what so if a piston gap valve, for example, will achieve good results in a lot of applications, but is going to struggle particularly at a lot of nano applications. But having said that, the formulation that goes into the product is just as important as having the equipment to smash it down in size. So if you have the right surfactants and other chemicals in your mix, you may be able to achieve a much better nano emulsion and achieve it at lower pressures than if you are not good on your initial formulation. So but definitely experience shows that piston gap valves will get you to a good level of reduced size in many cases, but they won't always get you to the smallest size. But if you have the right formulation with some easy to reduce emulsions, you can still get good nano emulsions off a piston gap valve. There is, as I've tried to say, there's no one solution for all applications, and it's a combination of the mechanical system, the homogenizer, and the formulation technology.
Yeah. So shall I take another two questions, Mark?
Yeah,
Is it
yeah,
okay? Yeah.
yeah. Fine.
So is there any thumb rule according to viscosity? How much pressure is required?
Not really according to viscosity, but the viscosity has a very significant effect on how you process, because when you process in a piston gap valve, the valve gap is a function of flow rate and viscosity. And as all of these devices are looking to achieve high shear, if the gap between the valve needle, valve piston, and the seat opens excessively, because to pass the high viscosity, it at a given pressure and flow rate will be a bigger gap, then you will lose shear in the middle of the shear channel. So viscosity, having high viscosity is not always good in terms of using a piston gap valve, because you will lose shear in the middle of the shear channel. So you won't have such a uniform shear. And then on micro channels, the higher the viscosity, the harder it is to get the product through the channels. So the more channels that you need to process the product. So there's no direct relation between viscosity and pressure, but there is a very significant relation between viscosity and shear that you achieve.
Yeah. What is effect of homogenization on the nutritional factors of food?
Oh, now you're asking me an application question, which I don't really have the answer. You would need to be aware, for example, in the ultra high pressure homogenization application, that the extreme temperatures may have an effect on the nutritional effect of your food, the nutritional value of your food. So there's usually a balance in a lot of these processes between the effect of the temperature affecting the food and the effect of the homogenization, reducing particle size. But if we took the example of the ultra high pressure homogenization, one of the advantages of that is seen as, because it's a very short duration heating cycle, 0.1, 0.2 of a second, to heat up to sterilization temperature, you can achieve a product which still has a lot of the textural and flavor and color properties that you would like to see in the food. So it's less thermally affected than a traditional heat sterilized product. But
yeah, sorry to interrupt, Mark. So here I would like to mention that a couple of our customers in India are using our ultra high pressure homogenizers to increase shelf life of fruit juices, natural fruit juices, without having any additives added into it or any other chemical or thermal processes. So it retains texture, flavor, and nutrient content. At the same time, it gives you excellent shelf life.
Oh, very good. Nice.
Yeah. Sorry,
Okay.
Yeah, no. I mean, it's a whole extra area, and I really, I didn't do a lot on the applications, and I kept away from the preservation technology of ultra high pressure homogenization. But if anybody wants to know more, if they just contact Sudhir or myself, we have quite a lot of information on various aspects of the high pressure homogenization processing overall for different applications.
Thank you, Mark, for your wonderful presentation and explanation with even a couple of videos also. And we had a very good interactions between our participants chat live. If anything, any clarifications from the participants, please contact to the Sudhir or contact to the Mark or Himatrao. So on behalf of the University of Agricultural Sciences, Karnataka, India, and Center for Nanotechnology, I wholeheartedly thank you to Mark and thank you to Himatrao and thank you to Sudhir and team of BioZ India Private Limited. Thank you very much, Mark, for your wonderful day.
Thank you very much, sir.
Very welcome. Thank you.
And made a day wonderful. Thank you. Thank you very much.
Thank you very much for this opportunity, sir. Thank you very much.
Yeah. Bye.
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 Bye-bye.
Thank you. Bye. Bye. Thanks.
Yeah, respected participants, we have another session with FTIR. I think Dr. Dilip Rawat is here. Dr. Dilip, can you hear me? Dr. Dilip?
Yes, I can hear you, sir.
Yeah,
Can you hear me?
Yeah, thank you. Thank you. Your voice is perfect. Can you turn on your videos if you don't mind?
Sure, sir. Sure, sir.
Yeah, this is Dr. Dilip.
Yeah.
I heartily welcome Dr. Dilip for in the afternoon session of day third, the role of nanotechnology in food and agriculture. So he's going to explain on FTR applications in especially in the food as well as in the nanotechnology field. Dr. Dilip has received his bachelor's degree in chemistry and master's degree in organic chemistry from University of Mumbai. He completed his PhD degree in organic chemistry from Shivaji University, Kolhapur, on synthesis and application of ionic liquids. He has done his postdoctoral studies from Korean Research Institute of Chemical Technology, South Korea, and also he did his at Sweden also. In his career of 11 years, he has worked in industries and academia under various capacities as a scientist, as assistant professor, and as an application specialist in a different industries also. He is a current role as a food product application specialist. He visits customers and solves the whatever the problems in terms of technical as well as the applications. And he does the discussions with the customers and the configuration build up a vibrational spectroscopy product with infrared, Raman, and UV spectrometer. His field of expertise is metal characterization using vibrational spectroscopy and FTIR. Now over to Dr. Dilip Rawat. Dr. Dilip, please.
Yeah. Thank you, sir. Thank you very much for the introduction. First, I would like to say, happy Ganesh Chaturthi to everyone. And I hope that you guys and your families are safe in this pandemic situation. So with this, I would like to begin my session on the advancement in FTIR and its application. So in today's session, I will be basically talking about the some basics of the FTIR. I'll talk about the sampling methods that are used in the infrared spectroscopy, and then I'll also talk about in between the applications that are there for which the FTIR can be used. So when you talk about vibrational spectroscopy, there are two types of vibrational spectroscopy. One is the infrared spectroscopy and Raman spectroscopy. Vibrational spectroscopy in totality is being used in variety of applications from the characterization, the material characterization, as well as for QA/QC application from say an R&D level to the plant level. So it has a wide range of applications of the vibrational spectroscopy across the various platforms. So let's begin with the basics of infrared spectroscopy. As we had a session yesterday from Amit sir on UV visible spectroscopy. So similar to it, it's the infrared spectroscopy as well. As you look at the light spectrum, the wavelength increases from X-rays to the radio waves, while in terms of wave numbers, it increases from X-rays to radio waves. After the visible range, what comes is the infrared region. Infrared region is typically divided into three parts. The first one is the near IR range, which is one which is close to the visible range. In terms of wave numbers, it is from 12,000 up to 4,000 centimeter inverse. After the near IR range, what comes is a mid IR range from 4,000 up to 400 centimeter inverse. And after that, what comes is the far IR range, that is from 400 centimeter inverse up to say 50 or lower centimeter inverse. Now, basically, when you talk about an FTIR spectroscopy, mostly people talk about the mid IR range of the infrared spectroscopy, from 4,000 to 400 centimeter inverse, basically where you get the fundamental bands of the molecules. However, the near IR range as well as the far IR range are also important, and they have their own applications in the field of chemistry and others. Uh, yeah. So basically, what is an infrared spectroscopy, or what happens in infrared spectroscopy? As I said, it is nothing but a vibrational spectroscopy. That means there is a change in vibrational level from the V0 state to the V1 state occurs when the molecule absorbs the IR radiation. So this is what is the infrared spectroscopy. Absorption of infrared radiation causes the vibrational or a rotational transition in the molecule. So when does a molecule can absorb an infrared light? There are two basic rules if the molecule follows that it can absorb the infrared light. The first rule is that the frequency of a light must be identical to the frequency of vibration. Typically, we consider the molecule as a spring, and when the two atoms are coming closer and going away. So when this frequency of vibration is identical to the frequency of light, it absorbs the light. However, there is one more important rule that also it has to follow in order to absorb the infrared light, which says that the dipole moment of the molecule should change during this vibration. So if there is a vibration like a spring, the molecule, the atoms are coming closer and they're going away. If there is a change in the dipole moment with that moment, then and only then it will absorb the infrared light. For example, an HCl, which has its own dipole moment, when the atoms are coming closer and going away, it causes the change in the dipole moment. While in case of nitrogen, when the two atoms are same, this moment won't cause any change in dipole moment, and nitrogen is inactive in infrared light. As far as the absorption of light is concerned, the atoms, the bonds which are made up of small atoms, absorbs at the higher frequency, while which are the bigger range or bigger atoms like metal atoms, they absorb at the lower frequency, what we call as the far IR range. There are types of molecular vibrations. There are two types, basically stretching vibration and bending vibration. Stretching vibrations are typically two types of vibrations, that is symmetric and asymmetric, while the bendings are like rocking, or scissoring, like scissor movement, open and close like scissoring, or a wagging or a twisting. All these vibrations can result in the absorption of infrared light, and you will see an absorption peak in the infrared spectrum. Just to give an example, yes, yeah.
There is some sound problem. Did you turn on any fan or something like that? Because
Just a moment. Give me a minute.
Yeah, please.
Is it okay now?
Yeah, perfect.
Yeah, great. So just to give you an example of the vibration in the methane molecule, this is the symmetric vibrations when all hydrogens are going away from each other. This is an asymmetric stretching, while this is the symmetric bending, while this is the asymmetric bending when two atoms are coming closer and then these two are going away. So the keys to the infrared spectroscopy basically is that the absorption occurs only at the characteristic frequency of vibration. So if it is matching to the absorption light, it absorbs. So therefore the infrared spectrum is a typical spectrum of that particular compound. Secondly, the position of the absorption peaks determine, as I said, the mass involved. Smaller the mass, it absorbs at the higher frequency, while the higher the mass, it absorbs at the lower frequency in infrared spectrum. Typically, what you see is that infrared light falls upon the sample, absorbs the light. Whatever light is being transmitted is being detected by the detector, and what you see the spectrum as a transmission spectrum. This is a typical vibrational mode. So this is an ethyl acetate molecule. This is the CH stretching that I was talking about. It absorbed around 2930 or 50 around, while stretching because the stretching vibrations, when you talk about, they are basically above 1200 up to 3600, while the deformation bands are from say around 15 below 1500 centimeter inverse. So here this is the deformation of the CH bond, and you see it at around 1430 centimeter. So centimeter inverse, and that this is how you can get the information. It's a chemical specific information that you get from infrared spectroscopy, by which you can use to understand the molecule. If it is unknown or if it is known, then you can do a library search and understand what kind of molecule it is. Understanding of the chemical information is possible using infrared spectroscopy. Now let's begin with the instrumentation of the infrared spectroscopy, how the instrument work. So before the coming up of the FTIR, that is Fourier transform infrared spectroscopy, initially it was a dispersive infrared spectroscopy. That means the wavelength, it has been scanned of one after the other. However, after the invention of Michelson interferometer and the Fourier transform, it has the Fourier transform into infrared spectroscopy is the common now, and it is what is being used nowadays. Typically, when you look at the Michelson interferometer, it has four parts. First part is an IR source. Second part is a beam splitter. The third one is the mirrors. There are two mirrors, fixed and moving mirrors, while the fourth one is the detector. So IR source typically gives all IR light that falls upon the part called beam splitter. And as the name suggests itself, it splits the beam into two. One part of the beam goes to the fixed mirror. So it covers a fixed distance from the beam splitter to the fixed mirror, and then it comes back towards the beam splitter. While the other part of the light goes towards the moving mirror, and then it is reflected from it and then comes towards the beam splitter, and then it interacts and goes towards the detector. Now, as the other mirror, as I said, is a moving mirror, as it moves from one part to the other, because of which the distance between the beam splitter and the moving mirror changes. And therefore, when this distance between the beam splitter and the two mirrors are same, what happens is the constructive interference, while when it is not same, or it's a different one, then what happens is the destructive interference. So typically what you get in an infrared spectrum as a raw data is the interferogram, which typically a time domain, which is then converted into a readable form or in terms of wave numbers. However, when you're getting an infrared spectrum, you have to take first the background spectrum, and then you take the spectrum of your sample. And therefore, first you get the background Fourier transform into the spectrum, single beam spectrum, while then you take the spectrum of your sample. And finally, what you see actually on the screen is the ratio of this background versus the sample, where the background is eliminated, and what you get is the spectrum of your compound. Typically, as I said, there are four components. The main components are the source, beam splitter, and the detector. So the first is a source. Typically, at what range in infrared spectrum you're working with, you choose the source. For Thermo Fisher, we use the Everglow source. For the range from mid-IR, far-IR, and some range of the near-IR from 9,600 to 20 centimeter inverse, while for the near-IR and visible region, you use the cord halogen as a source. The important part is again a beam splitter. Typically for a mid-IR range, the beam splitter that we use is a KBR beam splitter, which is which reflects light in the range of 7,400 up to 350 centimeter inverse. For a far IR, you go to the solid substrate, while for the near IR, you use calcium fluoride as a beam splitter, which has a range from 14,500 up to 1,200 centimeter inverse. The detectors that commonly use in most of the FTIR instruments are DTGS KBR a detector, which covers the range from say 12,500 centimeter inverse up to 350 centimeter inverse. The other common detector is the MCT detector, which covers the range from 11,700 up to 400 centimeter inverse, depending on the material used. So this is how, depending on the which range you're working with, and which all depends on the what kind of application you're looking at, you choose the different optics for your infrared spectrometer. So as I said, typically, if you're looking for information of the structure and identity, which you get it from the mid-IR range, you work with mid-IR spectroscopy. While if you're working with inorganic compounds or say polymeric modes you're working with, then you go for a far IR range. While when you're working with the raw material identification or some chemometric analysis, then you work with near IR range. So the typical application of infrared spectroscopy is the the qualitative analysis. It is basically used for compound identification. Because what infrared spectroscopy gives you the information of the functional group that are present in your compound. So if your compound is completely unknown, you have to use some information from infrared spectroscopy along with the information from NMR and the mass spectroscopy and some other spectroscopy. Combining that information, you will get the complete picture of your molecule. And infrared spectroscopy plays a very good role in giving you that information of functional groups that are present in your compound. As I said, the infrared spectrum is typical to every molecule. You can use it even for say a kind of a library search. So if you have a material, if you have a certain material in your library, you have already taken a spectrum, and if you're making it again and you want to know whether you have made it, then just take a spectrum of your new material, match it with your authentic one, and then if it matches, yes, it is the compound. If it doesn't, that means your compound has not been formed. So this is how you can use the infrared spectroscopy for a qualitative analysis of your compound sample. Infrared spectroscopy can also be used for quantitative analysis of your samples, because it follows the Beer's law. Absorption is equal to molecular absorptivity into path length into concentration. So if these two are constant, the molecular absorptivity and path length are constant, then absorption is directly proportional to the concentration. So that we can use FTIR as a qualitative analysis technique. However, when we have to keep it in mind that this is the secondary technique of quantification. So it relies on the information from the primary techniques like HPLC, GCs, or the other techniques which are more sensitive for the analysis, or it can go to very low level of analysis. However, once you get that information and correlate that information with FTIR, or infrared spectroscopy information, once you correlate that and you make a calibration curve, well, then the FTIR can be used as a quantitative technique for analysis. Why do people use, even if we have an HPLC and JCs, and FTIR is also used very widely for quantification technique, is because FTIR analysis can happen in minutes. You put the sample, you get the spectrum in minute. While in the primary techniques, it's take a longer time. It is more, method intensive process of doing that analysis. Here, you sample preparation is not that much, and you get the analysis in a minute. So if you have a calibration curve, you run your sample on an FTIR, and you can have a quantification result of your sample. And that's why it's a very good technique for quantitative analysis as well. So as a vibrational spectroscopy, basically it is used for qualitative analysis to identify unknown materials. If you want to understand the composition, if it is known material, you can understand the purity, the type of compound it is. You can, from that, that information you can get it. You can also use to understand the mixture or the contaminants that is there, as well as to understand the finished product, material distribution. You can also use it for the kinetic studies as well to understand how the process is going on. And as I said, it can be used for quantitative analysis, even if there is a multiple ingredients in the complex mixture as well. Now let's begin with the sample analysis and the application. So, how shall I choose my spectrometer? Now, as I said, it all depends on what is your application. So if you're looking for the applications like surfaces, mixtures, bulks, kinetics. So if you're looking basically for the structural information of your compound, you work with mid-IR range. And while if you're working with inorganic compounds or metallo-organic compounds, you work with far IR range. While if you're working with the bulk compounds, so known material, you want to understand the purity and what type of components that present in that compound, you can use the near IR spectrophotometer. Along with these typical basic spectrometers, there are certain hyphenations that are possible. For example, if you have a failure analysis or deformulations that you want to understand what went wrong with your sample or what is happening, what kind of components that are there. If you're using a TGA, then you can couple it with IR, and then now you can use both informations to get the more more analysis of your data. So there's integration of or hyphenation of TGA with IR is a very good technique for various applications. As well as you can hyphenate your GC with infrared spectroscopy to get certain information or like isomers or trace analysis. You can also couple a microscopy, and I'll talk about it further as well in my few next slides, that microscopy can be attached with FTIR, and then you can have the analysis at micron levels of your molecules, of your sample. It's a very good technique to do the analysis at a very low level. The another important hyphenation or an integration of FTIR can be with Raman. Raman is another vibrational spectroscopy, also involves in the change from the lower vibrational level to the higher vibrational level, just as of the infrared spectroscopy. However, it happens or it works in a certain different way, and therefore the one which are not infrared active are Raman active, while one which are not that much Raman active becomes the infrared active, and therefore both of these techniques are considered to be a complementary technique. By when you get the information from both the techniques, you can have more information, or you can have more analysis of your sample. Raman can be used for crystallinity, physical properties like crystallinity, density. It can be also used for identification of certain molecules. It is very good for identification of inorganic molecules, as well as it can be used for screening. So this is how you choose your spectrophotometer. Spectrometer. However, it is not only for a sample analysis. It doesn't end there. It's just having a spectrometer, IR spectrometer is not enough. What is important is you also have to have certain accessories that has to have along with your spectrometer, IR spectrometer. That depends on what is the physical state of your sample, whether it's a sample is solid, whether your sample is liquid, or you're working with the gaseous samples. Also, it works with the format of your sample. You have to understand what is the format. Are you working with powders or films or on monolayers, or how much your sample? Are you working with a bulk sample, or are you working with a microscopic sample? What you want to understand from the mixture, if you have a mixture, you want to know the major component, minor component, trace component, and also if you have few samples or you are doing many samples in a day, depending on which you choose your accessory. There is another important the consideration that we have to keep in mind when we are choosing an accessory is that what kind of sample analysis method are you going to use? There are two basic sample analysis methods that are used in infrared spectroscopy. The first one is a transmission method. It is just as simple as the infrared light passes through the sample, and then transmitted light is being detected by the detector. That's a transmission mode of a sample analysis in infrared spectroscopy. The other type of the sample analysis mode that is used in infrared spectroscopy is the reflectance mode of sample analysis. There are two basic modes in reflectance analysis. The first one is the internal reflection of IR light, So it is called as also as attenuated total reflectance, that is an ATR. So you must be using this buzzword of an ATR all the time. This is what it is, attenuated total reflectance. The other type of reflectance methods are which are called two methods, which are also called as external reflectance method. But what I mean is, herein the light is reflected from the sample, and there are two types. One is diffuse reflectance, the other one is a specular reflectance. Now, transmission method is the well-known method being used from the beginning of the infrared spectroscopy. ATR method is now been very much popular because of its own advantages of no sample preparation, while diffuse reflectance and specular reflectance are the typical sample analysis methods which are used for certain applications. And typically for example, like catalyst or soil analysis, diffuse reflectance is a very good method of analysis. So let's go through the sample analysis methods one by one. The transmission method, as I said, the IR light passes through the sample, and then the light is transmitted, and you get the infrared spectrum in terms of either a transmission spectrum or an absorption spectrum. Importantly, it can be useful for all types of samples, whether it's a gaseous samples, liquid sample, or solid samples. It gives you an excellent and a clean spectra. It's a spectrum, very good method of analysis. However, it associated with a sample preparation, and therefore the sampling handling is the key when you're talking about a transmission mode of analysis. You, in terms of solid, when you're working with solid, you have to make some KBR palettes, and one has to consider certain things when you're making palettes. For example, like you have to take around 1 to 2% of your compound, mixed with the KBR, and then you put it in the dye set, and then you made sufficient pressure. It requires a skill in order to make these palettes. So also with the liquid cells as well. So you have to take certain care. It takes certain times, requires skills in order to make a sample for a transmission method. But as I said, it's a very good method of analysis. Many SOPs are based on the transmission method. Good for many quantitative analysis, good for qualitative analysis as well. It follows the Beer's law very nicely. One of the example is I just wanted to show you this card now. This is called an IR card. For example, if you have samples like grease, where it's very difficult to make sample preparation. So here is just you put a grease on the top of the card. Well, onto the IR card, and then you can have a contaminant search with this is our software, Omnic Spectra, excellent software, and then you can analyze the grease and understand what kind of components that are present in a sample, like even in the grease. But other methods, you can use the KBR pellet or the liquid cell for the solids and liquids of your type of samples. The another important method of analysis, as I said, is, and very popular nowadays, is an ATR sample analysis method, which is called as attenuated total reflectance method. Typically, if you see here, as I said, it is an internal reflection method. So what happens in the ATR is that the IR light falls upon, so it is reflected inside a crystal. So it falls upon the crystal in such a way that it is internally reflected inside the crystal. And the point at which it is reflected at the surface, the electric field of the light extends outside, which is known as an evanescent wave. Evanescent wave of the IR radiation. Now, this is what interacts with your samples. Basically, in an ATR mode, you put the sample on the top of your crystal, and when this evanescent wave interacts with the sample, and then the light then goes towards the detector, carrying that information of the interaction of evanescent wave with the sample, and you get the infrared spectrum. The distance that it will travel in the sample is what is known as depth of penetration. So if you want to use the Beer's law, then this depth of penetration is the path length of your infrared analysis. So typically, I'll just go back to my previous slide. Typically, when you look at the ATR, you see a crystal here, and you see a pressure arm here. So when the ATR can be used for solids as well as for the liquids. It cannot be used for the gaseous samples. So what you do when you're using solid, it is very important to put the solid on the top of the crystal and then use this pressure arm, which is very important. Because when you're doing an ATR analysis, it is as I said earlier, that the point of reflection from which the evanescent waves are going out of the crystal, and it is very important to have that intimate contact of your sample with the crystal to get that infrared spectrum. This is and this in terms of solids, which can be very uneven, which can be granular, or film, which is a wavy kind of a film, or a sample is not that not homogeneous or something, then you have to use the pressure arm. So normally, if you're doing an ATR analysis, you keep the sample on the top of the crystal and then slowly move the pressure arm down and down till you get a very good spectrum, and then you start analyzing that sample. This can be, as I said, used for the layered samples, can be used for lumps, can be used for powder as well as liquid. In terms of liquid is always in contact with the surface, and there you don't have to use the pressure arm. Well, some of the precautions you have to take: cleaning the crystal off once you're done. Just take care of the acidity and basicity of the sample, depending on what kind of an ATR crystal you're using. So just see what kind of crystal you're using. Accordingly, you can keep your sample on that crystal and do the analysis. There are two basic types of ATR crystals. One is a single bounce crystal. One is the other one is a multi-bounce crystal. When I talk about single bounce crystal, that means it's a single reflection in the crystal. While the multi-bounce, it is a multiple times the reflection is happening inside a crystal. Typically, for most of the molecules, organic molecules or inorganic molecules, which are strongly absorbing in infrared light, people typically go with a single bounce crystal. Very good for most of the organic compounds, very good for powders, droplets, and flakes. People use multi-bounce crystal only when they need a larger contact with the sample. For example, if you have a dilute sample, so that means your concentration is less. So talking about the Beer's law. So absorption is equal to epsilon, that is molecular absorptivity, into path length into concentration. So if your concentration is less, so your absorbance will go down. So in order to increase the absorbance, you cannot change the concentration. So what you can change is the path length in the infrared analysis, and that path length in ATR can be increased by either changing a crystal, or you can increase basically by this multiple bounce. So here, if the evanescent waves are going one time, so this is the one times the path length. If you increase the bounce or the reflection number, increase that number, the path length will increase with this number of reflections. So it can be used for compounds which are less IR absorptive, or which are for the dilute solutions. Now, there are different types of crystals that are there in ATR, and typically people use the germanium, zinc selenide, and diamond. But how to choose appropriate an ATR crystal? Now, typically, most of the time, people use diamond as an ATR crystal because of its inherent properties of being a very robust crystal. It can work from the pH 1 to 14. The scratch-free kind of analysis is possible even if you have a hard material. The diamond can sustain it, and therefore it is mostly being used. However, there are people using zinc selenide as well, but then you have to take care of the pH range. As well as the germanium. Germanium is also being used. Typically, I just want to explain here is that the refractive index of the crystal is inversely proportional to the depth of penetration. So in terms of diamond, the refractive index is 2.4 and the depth of penetration is 2 micron. So if you have a compound which is very, very strongly absorbing, like carbon compound, carbon filled polymers, if you have like black polymer, which has a lot of lot of carbon, then it will absorb very strongly and absorbance will be really high. So what you can do in that case, you can reduce the path length, and the reduction in path length in ATR is only possible by changing the crystal to germanium, which has the lower depth of penetration. So there are certain applications. So depending on what kind of applications you're working with, what is your need, you can change or you can use a particular ATR crystal. Diamond works really well for most of the time. Just to give you an example or an application, just to have just to differentiate between the multi-bounce and a single bounce. Here is the used oil. When a single bounce was used, this compound has a very less absorption, so one did not see a peak absorption peak with a single bounce. But with the multi-bounce, you can see a peak. That up to 12 bounce crystal was used in order to see a peak. So this is typically if the compound has a very, so this particular material was at very low concentration. So in order to get it, they use the higher bounce crystal. One of the example as far as the food is concerned, so ATR, as I said, has been used in various, in various type of applications, and it is the technique is nowadays is used because it does not require sample preparation. You can just take a sample as it is, put it on the crystal, run the experiment, and you will get the infrared spectrum. Now, this is one of the example of the food protein powder for FTR with the ATR technique has been used to analyze the food protein powders for their classification and discrimination. So there are different types of protein powders that has been analyzed. For example, milk, peanuts, and rice, and this is from whey. Different types of vendors have been used. Different types of number of samples of particular vendors have been used. Typically, when you're looking at a fruit protein identification or quantification, you look at these regions. The different proteins absorb at different types. Amide 1, which is at around 1700 up to 1600 centimeter inverse, while amide 2 band, which is say from 1580 up to 1510 centimeter inverse. And the difference is because of their second when you're doing a protein analysis, you also look at the carbohydrate content, which is of the protein, which absorbs at around 1080, while these lipids are absorbed at around 1745. So you can see by looking at the structure, looking at the infrared spectrum of your compound, the proteins that are present in different types of samples have different types of, different concentration of lipids. They have different types of amide or protein structures that are present. You can see here the ratio of amide 1 and amide 2 is different for different samples. And also you can see there's a different carbohydrate components concentration is present in your sample. So using infrared spectroscopy, you can do the analysis of different components that are present in your food material. For example, you can see here, this is for the milk samples, 3 milk samples of a different, same vendor, but the different batches. It has different type of the carbohydrate concentration. Well, here in the peanuts, you can see the different types, concentration at the different peaks, which indicates that they are different with the different sources. Similarly, you can see it for rice as well as for the whey protein as well. So this is how you can use this information, and having this information of the particular sample at this different concentration. So if you make a calibration curve of these at a particular wave number or particular peak, that particular compound can be quantified using that calibration. So it's just such a nice technique for identification as well as the classification of your compound, as well as the discrimination of the different types of the proteins with the sources, as well as for the quantification of the a particular type of components that are present in your sample. As I was talking about, apart from ATR, which is an internal reflection method, there are other two methods of reflection which are known as the external reflection methods. There are two types basically. One is a specular reflection, the other one is diffuse reflection. Now, specular reflection happens when a light is reflected from a smooth surface. So if you have a very thin film, which is very flat and very smooth, the specular reflection occurs. Specular reflection, while in case of diffuse, it is from the rough surface, and the light tend to reflect from all directions. So you can see here, this is the static, kind of a lake. When there are no waves, you can actually see the reflection of the sun in the water, and that is what is called as specular reflection. While here, it's a rough surface, and you don't see a kind of a reflection of a sun in the water. So that is the typical example in the day-to-day life. So in a specular reflection, it follows the rule of light of reflection. That is, the incident angle is similar or is same as that of the reflection angle. And then it follows, it gives you a specular reflection. And I think yesterday I may talk about it when he was talking about the diffuse reflection as well. So the light is diffused in a rough surface. The light gets scattered, or it has been reflected in all the directions. Diffuse reflection is a very good technique for the sample analysis when the ATR or a transmission method doesn't work well. It is a very good method for matte paints or the packed powders or the etched metal surfaces. It is a good method for soil analysis. Diffuse reflectance is a very good method when people do the analysis of soil, which is the material which is very can be a very grainy material, and may not the ATR analysis may not be that feasible at times. So just to give you how does it work? Basically, when you're doing a diffuse reflectance spectroscopy, you dilute your sample again around 1 to 2%. You can go up to 10%, but start with the lower concentration, mix it with the diluent, either a KBr, any infrared non-absorbing material, and then when the infrared light falls upon it, and when the light is passing through this mixture, it is mainly reflected from the KBr particles, and when it is moving around, it also interacts with the sample and carries that information and gives you that infrared spectrum. Very good for the samples like soft powders or powdered mixtures. For hard polymers or rigid polymers, it is a very good technique to be used. Just to give you an example for soil analysis, as I said, it is a very good technique for soil analysis. Just a moment. Yeah. So this is the humene sample. So this H total whole sample H is the solid line, while the other two are the samples which after the soil residue after alkaline extraction. So one is the H humene and the other one is Bu humene, depending on how they have done the alkaline extraction. So now you can see here after alkaline extraction, you can see there is a reduction in this peak 1720, which typically talks about the presence of carboxylic acids in your soil. So by doing this kind of analysis using a diffuse reflectance method, you can understand what type of components that are present. For example, here this soil must have the presence of carboxylic acid. Also, there is a reduction in peaks at around 1600, which talks about the aromatic compounds. So that means your lignin was present. So this is how people can do the analysis of their soils and understand what kind of components that are present in their soil by doing the infrared spectroscopy analysis. The other method that I use is as I said, is a specular reflection used for the typical flat films, if they and can be used to analyze those. For example, this is an example of spray-coated polyester film on steel or aluminum film, and by using a specular reflectance, you can understand what kind of film that is present on your material, or what kind of sample that is present on your material. The other types of sampling methods are liquid. For liquid, we use a liquid cell. Either you can use a fixed liquid cell with a fixed thickness, or you can have a demountable cell with the different types of spacers so that you can change the path length of your liquid cell, and can be used for various liquid sample analysis in a transmission board. Similarly, for gaseous samples, you can use the gas cells. Can be from, you can go up to 100 millimeter or 10 centimeter. Various types of gas cells are used depending on the application. So you push the gas from here, and then it goes out from here, and then you can do the gas analysis using the transmission board with the gas cell. Mostly when people talk about the infrared analysis, they basically talks about the mid-IR range. However, the far IR range, as well as the near IR range, is also very, very useful for analysis of the sample. Particularly the near IR range is very useful for food analysis of the food samples. Far IR range is, as I said, good for the inorganic material. For example, if you're looking at some material which are absorbing only in far IR range, you have to use the far IR spectroscopy. Near IR range can be used, and it is a very good technique for quantification of your samples. For example, if in the food samples, you want to understand how much is the protein, how much is fat, how much is moisture, or the ashes, or any other dry material is there. Near IR spectroscopy is a very good technique to get that information. Importantly, it can be used for aqueous solutions. It can be used for solids. It can, and the near IR, even if your sample is in the glass vial, or it's in the polymer packaging, still you can do the analysis of your sample using near IR range. And as I said earlier, the Raman is the technique that is being used also along with the IR spectroscopy to have that complementary information. Well, just to give you in a glance of how far IR has been used. Yes, please.
Sorry to interfere you. Is it maybe another 5-10 minutes?
Yes, I think, yeah, definitely.
Fine, thank you.
So our range, just a moment. Yes, so this is typically a kind of a yellow compound that is present in the polymer, which we do not want. Some compounds are banned. And if you want to understand what kind of component it is, then you, from a mid-IR range, you typically don't get the information. You now here, from here, you can see the molecule that is present is a polyethylene along with calcium carbonate peaks in it. But calcium carbonate doesn't give the yellow color. So from where the yellow color has come. And you can see when you run the far IR spectrum, it is basically it has an absorption in far IR region, and you can see that it matches to a cadmium sulfide, and now you know the cadmium sulfide is present in your sample. Just have to give you some examples of near IR spectroscopy. As I said, it is a very good method for food analysis. It is not like a fundamental bands. As you see in mid-IR, you get the combination bands and overtone bands, which are used for the analyzing of different samples. Typically, you will use the integrating sphere, or you can also have a fiber probe connected to near IR, and you can have a remote analysis of your sample as well. So you can take the probe towards your sample and do the analysis. And as you can see here, the sample is packed. So even if it is packed, you can do the analysis of your sample using near IR range. So near IR basically has been used extensively for food and analysis of food and food products. For example, processed foods, the beverages, the grains, the fruits and meats. The common components that are identified are like protein, moisture, ash, starch, fats. And you can do it simultaneously without doing any sample preparation. So you're not even destroying your sample when you're using a near IR analysis. This is a typical example of a barley analysis, where with the different types of variations like regions, conditions, seed size, you can have different types of components that are present here. Is the typical moisture component. How amount of moisture has been, they have done a calibration curve, and now when you get the sample, you can understand what, when you have the supply from someone of the barley, you will understand how much moisture you have, and then you can put it for the further processing of your sample. This is another mode of way that, as I said, NIR is very useful even in the polythene bag. If you have a sample which is very viscous, even that can be used if you're using with NIR, and then you can use it. Here is the component A and component B in a syrup was being calibrated, and then you can just understand the component A, presence of component A and component B in your, how much it is in your sample. This is another example of the dairy kind of a sample. You see cheese that has been produced, how much fat, moisture, protein is there. You can analyze that using an IR. Otherwise, if you want to use do the analysis of cheese for these kind of components, it is a very toxic methods, noxious method. Here you don't need any of the sample preparation. So we say typically these kind of instruments are used. This is our Antares NIR, or that has been used, or you can couple the NIR with the instrument IS50 and do the analysis of the sample. I just want to go to show you another hyphenation, that is TGA. TGA basically can be used in soil analysis, where you keep the sample here, and the gas, then the gases that are producing TGA can be transferred to the IR infrared light, and you can get the spectrum of here. It's a water that spectrum you get, or in the next analysis you get the methane evaporated here. Any sample, gaseous samples, then passes through, and then you will get a typical infrared spectrum, and you will understand the chemical composition of that material which has been evolved, and that from which you can understand what was the component that is there. This is just an example of a gasket, however. There's one gasket which is good one is a good bad one, and they wanted to know which one is what had happened, what is the problem. They did the TGA analysis, and then at 67 minutes they took the spectrum. After subtraction, they understood that it is this isopropyridine phenol molecule, because of which so the composition was not good, because of which it was failing. I was talking about the hyphenation, another GC. Here is the GC hyphenation. The output of GC can be given to the IR, and then you can analyze it with IR and understand what kind of component it is. As I said, it's here. It's an isomer of xylene. It's showing it as a metaxylene component that is present. Another important aspect that I want to convey as well is the IR microscopy. Which is a combination of light microscopy with an FTIR microscopy. So when you have a samples which are in a very micron levels, or if you have a film of different materials, or a sample which is not homogeneous, and you want to understand the complete sample, what it is made up of, you can use the IR microscopy as well. So what happens here is, using light microscopy, you see the sample, a visual image of your sample, the optical image of your sample, and then you focus on the particular area, and you come to know what kind of chemical composition of that material you've identified, or you're looking under the microscope. So it can be used for new products, or if you want to understand the reverse engineering, you got some material, understand what kind of material it is, you can do the analysis, understand the material. It can be also used for failure analysis as well. This is a typical example of rock. So if you're doing a rock analysis, here is the the rock samples of different phases, and by doing the IR analysis, you can see what kind of sample and where, what kind of material, A1 or A2, and where it is present in the sample. Well, just to give you the last, that is a Raman example. Raman complements FTIR. Typically, mostly for inorganic compounds, it has been used because Raman typically works in the region when you're doing a Raman 3,500 up to 50 centimeter inverse. So that means it covers the far IR range as well, where the inorganic material absorbs. And so here is a typical example. So here you can see in your sample you have a Raman material, you have a TiO2 material. So they have taken the Raman spectrum of their bottle sample, and one of the peaks are matching with the TiO2, which is a rutile TiO2. It also matches with the anatase TiO2. So that means this sample contains the rutile as well as anatase TiO2. So you can have the information of your inorganic material. For example, like if there is a solid that is inorganic, you can get that information. Here is the peaks for calcium carbonate. So it gives you the indication of what kind of material that is present. So this is with this I finished my presentation. For the microscopy, I would like to tell that even the contaminants, which are in very small amount, you can actually see under the microscope, and you can understand what kind of chemical composition is present in your compound. So thank you very much for your kind attention. And if there are any questions, then we can take those questions.
Yeah, thank you very much, Dr. Dilip. So wonderful presentation. Can you stop sharing your slides if you don't mind?
Sure. Just a moment.
Sure. Yeah, turn on your videos so that you can have charts from the audience. So there is a couple of questions, Dilip. Shall I go ahead with the question and answer session?
Yeah, please, sir.
Yeah. What affects intensity of IR peaks?
Intensity of IR peak basically it's how much it absorbs, and it's how you have made the sample. Sample preparation is the key in the IR spectroscopy. So if your sample preparation is not good, if you're making a transmission mode of analysis, that can affect the absorbance. As well as if you're ATR, as I said, you have to use the pressure arm. That can affect the concentration, can affect. So there are different things that can affect the absorption peaks, the intensity of the absorption.
Okay. Did a radical polymerization took place in FTIR? Radical polymerization.
Means can we analyze radical? Yeah. So virtually no chemical reaction occurs with IR. So we can analyze. Yeah, we can analyze samples, radical polymerization as well. But there are different types of techniques that are used. We have to see how they are doing it. What is what is the construction of their cell or their what I call their what is the material of construction where the radical polymerization occurs. Depending on that, we can choose the right accessory, and then we can analyze the radical. So we can follow in situ monitoring of radical polymerization.
Yeah. Is it possible to use FTIR for all year, mid, and far? Yeah, it's possible.
Yeah, it's possible. FTR typically what we mean is the mid IR. FTNIR is the other one, and then we add far IR range to it.
Correct. Yeah. So it is mid and NIR, then far IR, right? So can we use ATR for gas sample too?
No, as I said, no, it's not possible.
Yeah.
It's basically used for solid and liquid samples.
Solid and liquid. Okay. Will long range forces influence on the IR and Raman spectroscopy?
Pardon, long range?
Long range forces.
Long range, sir?
Long range forces.
Forces.
Yeah, influence on the IR and Raman spectroscopy.
It depends. As I said, it depends on if it affecting the say particular bond. If it is a carbonyl bond or something that is present, and if it is affecting that bond, then definitely it can affect the particular peak intensity as well. or peak shift can occur. So if you have a mixture of particular compound, then because of the interactions, you can see a shift in the bands, maybe 2-3 wave numbers, but you definitely can see a shift depending on how there is an interaction between these forces.
Okay. For a particular wave number, how to interpret the multiple spectrums with their intensities?
Yeah, so that means if you're looking at the same kind of a material of a particular wave number, so if your concentration is increasing, that means your peak intensity will increase. That is what will happen, and that is how you can correlate the concentration information of that particular compound. So you associate that compound with a particular frequency, and then you see the absorbance, and then you can correlate it with the concentration, and then that's how you can use it for quantification analysis.
What is the difference between IR and NIR spectroscopy?
As I said earlier, it's a mid-IR versus the NIR, as I can say like that. In mid-IR, basically, you're looking at the fundamental vibrations. You get the different types of peaks for particular type of the vibration. For example, carbonyl will have a different vibrational frequency. OH will have a different vibration frequency, while if you have an ether, you have a different CO bond frequency. In NIR, however, you have these combinations and overtones, which are not as distinguishable as you see it in the mid-IR range. So this is how they are different. However, in NIR, the spectrum is very much, can be correlated with a particular compound, and then once it is a known compound, you can use it for the quantification studies.
Okay. Is FTR drift transmission spectra is larger than 100%?
FTIR?
Drift.
Drift, huh?
Yeah, drift.
Drift is?
Transmission spectra is larger than 100%?
No, it cannot be. You see basically, no,
it's not possible.
not possible.
Yeah. So how to identify and increase intensity intended molecule of any bio extracts? How to identify and increase intensity intended molecule of any bio extracts?
So that means you're looking at the change in concentration, basically.
Yes, correct.
Yeah. So basically, you correlate that information. If you see, it's when you're doing a quantification using a mid-IR range and the near-IR range, there's a little bit certain differences. In the near-IR range, you consider the whole spectrum as the spectrum of that compound, and you identify certain regions to and see the effect of overall effect in NIR. It's a little different way of doing the quantification analysis in NIR. In mid-IR range, you typically look for those vibrational frequencies which are associated with that compound, and then you see the intensity of those and do the quantification.
For a mixture of compounds, how FTR will be helpful? For a mixture of compounds?
Yes. So mixture of compounds, FTR is really useful. If you have a library of particular compound, say if you have a mixture of 5 components, and if you have a library of those 5 components, even if they're in different concentration, every component will have its own typical FTR spectrum. So if you do a library match, in the typical spectra, typical software like us in Omnics Spectra, we have a software which can do this multi-component analysis, and it will give you the list of all the components that are present in your sample by looking at those peaks. So what it will do is it will look for the major component first, then it will see, remove the major component and see what are the typical characteristic peaks that are there that will identify with the another component, and you will get the information of most of the components, like 5 to 10 components in your mixture using FTIR spectroscopy.
Okay. So I think somebody has raised the hand. Can I have the, so they have closed. Okay. Sampati, do you have any questions? Sampati Sojan. Do you have any questions? Okay, no issues. Okay, is there any questions to ask Dr. Dilip? It's most welcome. So there are a couple of questions, maybe around the, even I didn't find any questions in the, yeah, even in YouTube also. Thank you, the participants who have spent their time, that too, today is holiday. Can we identify the adulterant from food by using NIR spectra?
Yes, it is possible. Yes, it is possible. So if you have known adulterants, yes, it is possible
Yeah,
to do
only it is a known adulterant, then only, because it is very difficult to quantify it, right?
that.
Yeah. Okay, is there any clarifications? Is there any questions so that we can have maybe another 1 or 2 questions? So, or else, we can wind up the sessions. Yeah, I hope there is no questions in both YouTube as well as the Zoom chat box. Okay, so thank you very much, Dr. Dilip, for your wonderful presentation, that too on holiday today for you guys and for us also. And everybody is in the Ganesha festival mood, but in the pandemic situation, at least you make them to active and understand the FTR concept, basic principles, and what are the uses of the FTIR. So in the food industries as well as in the nanoscale, nanomaterials. So on behalf of the, our university, Center for Nanotechnology, and on behalf of the all the participants, I extend my sincere thanks to Dr. Dilip, Dr. Dilip, who has spent a wonderful, because again, he's going to have another session, I believe.
Yeah.
Yeah. So definitely, Dilip, if you anything come across, definitely we'll update you in the chat box or maybe in the next session for the
Sure.
question and answer. Yeah. So there
Sure,
are, if it is possible, can you share your presentation to my mail so that I can circulate among the participants, if it is possible, anything which is any confidential, you can delete it, or if it's general information, you can share to the participants if it's possible.
Sure, sir. I will do that.
Yeah. Thank you very much. Once again, I extend my sincere thanks to Dr. Dilip. Thank you very much.
Yeah,
So,
thank you very much, sir, for this opportunity. And I just please take care, everyone, and stay safe.
yeah. So, thank you. Bye bye. Take care. So, this is the information regarding to the our participants. So, thank you very much for your wonderful presentation, wonderful availability. Because in the starting we were reached 210, then come down to now it is 150 members. But actually we supposed to have almost 500 plus because total registration is 1100. But somehow I don't know why the participants probably there is maybe a Ganesh festival or maybe a holiday for them. But I'm sure that in coming days all the participants should be very active, and please make sure that your presence should be most important, because the speakers they are from the different parts of the company, even different parts of the country. So they are well prepared and they are doing their level best. So make use of this. Even in the pandemic situation, please have a knowledge and make use of these days. So thank you very much for all the participants for your wonderful day. Okay, take care, be safe. And tomorrow we have 2 sessions. So one is from Dr. Vinod Shaharan. He's going to start at sharp 11 o'clock. Biomaterial based nano formulations for agriculture. And second, in the afternoon session, we have a Dr. Karthik Balasubramanian. He's going to explain in XPS, advancement in XPS and its applications from the thermo. So please be there at sharp 10:50 a.m. in the morning and 2:50 p.m. in the afternoon for having interactions between our well-learned speakers. So I already shared the feedback form to the even in the June map, as well as in your Telegram and as well as in the YouTube channel. Kindly fill the feedback form and give your answers. Thank you very much. Good day. Take care. Bye safe and stay home. Thank you. Bye bye. Bye bye, Dilip.
Thank you. Bye bye. Bye.